All right, so the plan for today is to finish section 2.4, couple of problems left in 2.4, and then start on 2.5, working with equations that have fractions or decimals in them. So kind of building off of the general strategy, remember the general strategy from 2.4, uh, and looking at some modifications we can do, or I suppose a modification we can do that uh, got a chat message. Did you get my email? I think your email came in last night or yesterday. So I was catching up on my weekend emails. I got caught up on those, so I'll get to my emails from yesterday in my office hours or shortly after today. So you should get a response from me if you emailed me yesterday or early this morning. You should get a response from me, um, before noon today. Okay. Yeah. So looking at modifying our general strategy to handle equations that have fractions or decimals, maybe make them a little more approachable. Okay, the quote of the day today is a paraphrase of Ralph Waldo Emerson. It's not often that the paraphrase of a famous author is a little more punchy than the author's original statement, but I think in this case that is true. And the statement is, "What you do speaks so loudly that I cannot hear what you say." In other words, it's kind of like actions speak louder than words, but really driving that point home, really driving home the point that if your actions and your words are misaligned, it almost doesn't matter at all what you say because people will see the actions. And I think related to this idea, especially with it being January and kind of New Year's resolution time, things like that, something that I think is good to uh, check in with every once in a while. And I think this was a good exercise just to actually, physically write down answers to these things. Just for yourself. I mean, I'm certainly not asking anybody these questions directly, but something to think about yourself. Jot down a list or a paragraph for each. First, what things do you value most? So if somebody said, what's most important to you in your life? Write a paragraph or list 5 things or something like that. What would the answer to that be? And then asking, well, where do you spend the majority of your resources? In a given week, where do you spend most of your time, right? Where do you spend most of your talent, your maybe cognitive energy, your emotional energy? Where do you spend most of your treasure, your kind of spending money? And are those two in line? Is there a concordance between those two, paragraphs or those two lists, or is there some discordance? And I mean, I think everybody has a lot of discordance between their lists, so don't, get down on yourself. But I think it's good to check in every once in a while, especially these days. There are so many things vying for our time, time especially things like social media. It's so easy to say, all right, I'm going to take a 10-minute brain break, and then 2 hours later, you like poke your head up, you're like, wait, what happened? Yeah, or in some sense talent, right? There's a lot of things, even just these past couple of weeks, vying for our emotional resources and things that are getting people very, very charged up emotionally or spending a lot of cognitive energy on it. So, um, I think it's worth it checking in and asking, is there alignment between these two? And if you see misalignment, don't try to tackle like everything at once. I think everybody always has some misalignment or probably quite a bit of misalignment. Is there one place that you can make a little bit of headway? Can you put one of those app timers on Facebook or something? I've done that before when I realized that my Facebook time was getting a little out of control. So things like that you can do. Anyway, that's the quote of the day and some related thoughts for today. Okay, jumping into section 2.4. So just kind of revisiting this general strategy. Remember, the first thing we want to do is simplify, combine like terms, etc., to get down to this standard form, ax plus b equals cx plus d. And don't worry so much about the a bigger than or equal to c part, but mainly we're looking to get to uh, a variable term and a constant term on both sides. We don't want to have multiple variable terms or multiple constant terms on a single side. If we do, we should be able to simplify that expression by combining some like terms. The next thing we want to work on is combining the variable terms together. So if I have an AX term on one side and a CX term on the other side, I want to either subtract AX from both sides or subtract CX from both sides to get my variable terms together. So I only see one variable term across the entire equation. And I probably ideally want to keep that coefficient positive. Again, not the end of the world if that doesn't happen, but it does make things a little easier here. And in the future, a decent bit easier. When we start talking about inequalities, it's just easier not to have to deal with that negative coefficient. So we get our variables on one side, and then we get our constant terms on the other side. And at that point, we'll have isolated the variable term. We'll have, something like number times x equals number. We divide by the coefficient to get the solution. We isolate the variable itself, and then we plug back into the original equation and check our solution. Okay, so to start off today, jumping right into two exercises because we had covered this material last time. And remember that we have some special cases as well. We have conditional equations. So let me just remind you of this because we have had a weekend, and with these 2-day-a-week classes, and we've had a weekend, it's like 5 days since the last class. So we have 3 different types of equations we could end up with. The kind of most common type, the standard type, if you want to call it that, the one that we had spent a decent bit of time on is conditional equations. And this would be something like, x plus 1 equals 4. Oh, geez. X plus 1 equals 4 has exactly one solution. I was thinking in my mind the phrase exactly one solution and wrote 1. Has exactly one solution, x equals 3, because 3 plus 1 equals 4. No other value of x is going to work here. Plug in x equals 5 or -7 doesn't work. And we have found a value of x that does work. So there is a solution, and this is the only solution. This is called a conditional equation. This statement is true if and only if this is true, right? Saying like the ball is on the floor. Well, you look at the ball, is it on the floor? We can say, well, that's true if the ball's on the floor, but it's not true if the ball's on the couch or if the ball is on the table. We had 2 other examples. We had an identity, something like x plus 1 equals x plus 1. Typically, our identities don't look this simple. Maybe we have some uncombined terms on both sides or some parentheses on one side or something like that. But it turns out that any value that I plug in for the left side, when I plug it into the right side, I get exactly the same output. And that's very clear here. This is an identity. It has solutions, all real numbers. So x equals 3 would be certainly a solution. 3 plus 1 equals 3 plus 1, but so would x equals 10 or x equals -20. All values of x are solutions, even fractions or decimals. We could plug those in as well, also solutions. And then we also had contradictions. Something like x plus 1 equals x plus 2. Well, the right-hand side is always going to be exactly 1 larger than the left-hand side. And basically, since 0 does not equal 1, because something that's 1 larger can never be the same size as the original thing, these 2 sides can never be equal. If I plug in x equals 3, I get 4 equals 5. That's not a true statement, and that's going to be not a true statement for any value of x that I plug in. There are no solutions. So just keep in mind that we had those possibilities as well. So for these 2 exercises, work through this general strategy. Let me try to get everything on one screen here. I think I can. Like the tank engine, right? There we go. So work through this general strategy. Simplify both sides. Work your way down to a solution that might look something like this. Or remember what would happen in something like an identity if I subtract x from one side to get the variable terms together. I subtract it from the other side, and it actually cancels the x's off of both sides. I would get something like 1 equals 1. All of my x's disappeared, but I get a true equation. Versus for a contradiction, I would get, say, 1 equals 2. All my x's disappeared, but I get an equation that is false, that this is never true. So work through these two exercises, work towards a solution, and the solution could be a conditional equation with a single number as the solution, or it could be one of these other two cases. So take about, I guess take about maybe about 7 or 8 minutes for this, because there is a bit of simplification to do, a bit of work on the back end to do as well. So let's plan for about 7 minutes and we'll see. Maybe we'll take another minute if I think it's needed. But we'll come back together in about 7 minutes, work through the answers to these. And as always, remember, I'll have chat open. If you have any questions, pop them in chat. Or if you want to, you can unmute yourself and ask if that's easier for you. Okay, it's about 7 minutes, so let's take a look at these two. Um, so I didn't see many questions in chat, so hopefully that means that folks were kind of progressing pretty smoothly through these problems and didn't really get stuck. Or if you got stuck, maybe you took a look at what I was writing and that helped you over that bump. So again, the first thing we want to do is to get things in this standard form. That actually helps a whole lot with identifying identities and contradictions as well. Once we get it in standard form, it's often almost trivial to identify an identity or contradiction at that point. So for this one, we multiply out the left-hand side by distributing the 3. We get 5x. 9 times 3 is 27, so plus 27. And then 3 times 3x is 9x, so plus 9x on the left side. And on the right side, distributing gives us 14x minus 22. The left side, the 9x and the 5x, they're like terms. They can combine together, add to 14x plus 27 on the left, and 14x minus 22 on the right. And, especially if we've seen a few of these before, we recognize right away this has to be a contradiction. I have the same variable term on both sides, but I'm adding or subtracting different numbers. We're always going to be some distance apart, right? The left and right side can never be the same. But if we wanted to see that algebraically, we have now finished step one. We've got variable term plus constant term on both sides. We work to get our variables on one side. So maybe we move the 14x on the left to the other side by subtracting 14x, but we note that if we do that, well, our 14x minus 14x on the right side, we get rid of the variable term on that side as well. All our variable terms go away across the entire equation, and we're just left with an equation relating to constants. 27 equals 22. And remember that this equation, this statement here, 27 equals 22, has the same truth value as this one, or as this one, or as our original equation. But 27 equals 22 is never a correct statement. 27, 22, or actually that should be negative 22, sorry. It should be a negative 22. 27 equals negative 22 is never a correct statement. It's always false, regardless of the value of x that we chose kind of abstractly here, but more tangibly say here or here. This is never true for any x. Therefore, this is a contradiction. It has no solutions. There's not really a good way to check our answer here because you might say, well, maybe I could like pick a random value for x and see if I plug it in and if it works. Yeah, but I mean, if I pick a random value for x for a conditional equation and plug it in, it's almost certainly not going to work either, right? There's only one value of x that works for these conditional equations. So, picking one x or even a handful, three x's or some three different values for x, plugging them in and seeing if they work and seeing that none of them work really doesn't, help us a whole lot here. So there's not a good way to check contradictions, I don't think, other than just, if you wanted to check, you might go back and just verify your work. But we do indeed see that we get a contradiction here. No solutions. There are no values of x that lead to a true statement here. On the other hand, our next exercise, we do a similar process. We distribute, we simplify, we combine like terms. We've got step one done, and we have 12x minus 3 equals 12x minus 3. Kind of just by inspection, we can pretty clearly see that, well, the two sides are exactly the same. Whatever I plug in for x on, say, the left-hand side, when I plug it on the right-hand side, they're going to turn out to be the same number on both sides for any choice of x, whether it's 0 or 100 or negative 3/5, whatever it may be. But I can proceed algebraically if I didn't see that right away. I can try to combine my variable terms, maybe say by getting rid of this 12x on the left and, putting it on the right. But I see again, when I try to do that by subtracting 12x off both sides, well, my variable term on the left goes away, but my variable term on the right exactly goes away as well. And I get the equation negative 3 equals negative 3. I did have a message in chat that said Could we say, for instance, add 3 to both sides? What if I had added 3 here to get the constant terms kind of, with the idea of getting the constant terms onto one side? Yeah, that's fine. You would have down here got 0 equals 0. So that wouldn't have broken anything. As long as you're doing valid equation solving steps the whole time, then you're good. So if you had, tried to get your constant terms together first by adding 3 to both sides, that -3 plus 3 would have just netted out to a 0 on both sides, and you'd have got 12x equals 12x, and then you try to combine your variable terms, subtract 12x off both sides, you get 0 equals 0. Yeah, that's perfectly fine. But regardless of kind of which strategy you took, which path you took, or if you took a slightly different path, if you did even some other valid step, adding 5 to both sides or something, you would always end up with a statement like this where you get number equals same number once you get rid of all the x's. And this is a statement that is always true for all values of x. This is an identity. It has infinitely many solutions. In other words, when we say infinitely many solutions, what we really mean is that every value of x satisfies this. That's a slightly different statement than saying infinitely many solutions, right? We could have infinitely many solutions if like every positive even number satisfied it, it would still be infinitely many solutions. But really what we're saying when we say infinitely many solutions in this context is we're saying that every value of x, every real number x satisfies this equation. So my claim is that any value of x that I pick, when I plug into the original equation, should result in a left and a right-hand side that are the same. And I can kind of check this. Obviously I can't check all infinitely many solutions, but I can pick kind of a random solution, right? Maybe I'll just try x equals 0. I did that one here because it's easy to compute, but could do x equals 1 or x equals -1 or something if you wanted to spice things up a little bit. I probably wouldn't pick like x equals 17/3 or something. That's going to be kind of a pain to do the arithmetic to check. But if you pick, one value of x, or certainly if you pick 2 values of x and they both work, that's pretty good. That's very strong evidence in favor of being an identity. But if we plug in, say, x equals 0, again, which I picked just mainly for convenience, we're making the claim that all values of x work. So I should be able to pick whichever value of x I like, plug it in, and it should work. If I pick a value of x, plug it in, and it doesn't work, if I get, one side equals 5 and the other side equals 3, then I've done something wrong at some point, either in the work checking or in the work establishing it as an identity. But I do see that if I plug in x equals 0, again, which I just picked as an example to check, I see I get -3 equals -3, and I get a true statement. And again, if I wanted to really hammer this home, if I really wanted to provide a true proof that this is an identity, I could pick one other value of x, say x equals 1, go through the work and show that that also simplifies down to number equals same number, a correct statement, and then I'll really have thoroughly demonstrated it's an identity. Something that we might have noticed here that's maybe a slightly more advanced concept that we'll get to coming up a little later in the class or in the course. So we have identities and contradictions that have infinitely many solutions. That's an infinity sign, or 0 solutions. We have conditionals where some x's are solutions, but not all x's. The only conditionals that we've seen so far have had exactly one solution. And that actually is the case for these linear equations. If we're not in either of these situations, if we don't have 0 solutions and don't have infinitely many solutions, we have to have exactly one solution. There's no linear equation that has, say, exactly 2 solutions, but no more. or exactly 4 solutions, but no more. So in fact, if I came down here and I checked x equals 0, I know x equals 0 is a solution. If I checked x equals 1 and say I got to a point where I can confirm that x equals 1 is also a solution, I know that there are at least 2 solutions. So it can't be in the case of a contradiction because I found a solution, there aren't 0 solutions. And I can't even be in the case of a conditional because the only conditional possibility is having exactly 1 solution in this context. So showing that there are at least 2 solutions implies that we are in the identity case and we have infinitely many solutions. So that's a little bit more of an advanced concept. If you didn't completely follow that, that's perfectly okay. But I just wanted to point that out. That's the logic behind what I was saying, where, checking one choice is good. It's kind of helpful. But I mean, I guess this could be a conditional and you just got lucky and happened to pick the one value of x that satisfies it. But picking 2 and demonstrating that both of them are solutions is actually a proof that it's an identity, because it excludes the only other cases of contradiction and conditional, which have exactly 0 or exactly 1 solution, and 2 is neither 0 nor 1, so we have to be in the identity case. All right, any questions on 2.4? All right, so we are going to move into 2.5 now, looking at solving equations with fractions or decimals. And we're going to use many of the same tools and techniques that we've used so far, with maybe one minor change. So let's take a look at this equation. We have number times x plus number equals number. So ax plus b equals c kind of a situation here. And we know how to solve this. This is already simplified on both sides. We would get the variable terms together, but we only have one variable term here. We then want to isolate the variable term, getting that constant term, that plus 2/3, onto the other side. And after each step, simplify. And then we want to divide by the coefficient of x to isolate the variable itself, and then check. So I can solve this using that general strategy. I can, well, one, are we in simplest form? Yeah, both sides are simplified already. I don't have to do anything to simplify. Each of these expressions, the left and the right-hand side, are simple. 2, I want to get my variable terms together, but again, I only have one variable term across the entire equation. But then I want to isolate my variable term. I do that by subtracting off the constant term that's attached to the variable term. So if I subtract 2/3 from both sides, on the left, the plus 2/3 minus 2/3 goes away, and I get 1/3 x. And on the right, 5/3 minus 2/3, well, that's 3/3, or, well, 3/3 is just 1, right? I can write that as 1 instead of 3/3. And I've now isolated my variable term. My variable term, this 1/3 x, is by itself on one side of the equal sign, and everything else, all of the other constant terms, are on the other side and have been combined together, simplified. And now I can isolate the variable itself. And I see that my coefficient of x here is 1/3. So let me divide through by 1/3. Or I see that dividing by a fraction, and that's kind of cumbersome to deal with, but I know that that's the same as multiplying by the reciprocal. So let me write that instead. Instead of dividing by 1/3, I'm going to multiply by 3/1, or just really just multiplying by 3 in this case. So I'm going to multiply by 3 or divide by 1/3, however you like to think about it. On the left, 1/3 times 3 is 1. 1x or just x on the left. 1 times 3 on the right is 3. And is it true that 1/3 times 3 plus 2/3, that's 3/3 plus 2/3, that does give me 5/3. That looks good. So I went through my same equation solving steps as before. Exactly. And as Paul commented in the chat, we're looking to solve this 2 ways. We can use our equation solving steps, our general strategy from up here just as is. It works. But this is a lot of dealing with fractions, right? We had fractions in every step. We were saying, wait, I want to divide by 1/3, which is multiplying by 3. So I had to deal with fractions here. If you don't particularly like dealing with fractions, and I think most people would rather deal with whole numbers than fractions, what we can do first is eliminate the fractions. In this case, we're starting off with a simple case here. In this case, this 1/3 x plus 2/3 equals 5/3. This is my original equation. I could choose to multiply both sides by 3. That's a valid equation solving step, right? I could, if I wanted to, add 5 to both sides or divide both sides by 2, or if I wanted to, I could multiply both sides by 3. That doesn't follow our general strategy, but I could do it if I wanted to. That doesn't break anything. So let me multiply the left side by 3, and I'm going to be really careful when I do this. When I multiply the left side by 3, I multiply this entire expression, making up this left side. That whole expression gets multiplied by 3. So it's like I put a parentheses around the whole expression on one side and a 3 out in front. And then the same thing on the right side, 3 times this entire expression. In this case, the right side isn't too complicated, but if it was more complicated, put parentheses around the entire right side, multiply by 3. Yeah, exactly. So we're kind of multiplying by the reciprocal here. And that's kind of the operation that we're doing in the beginning here. Oh, now if I go ahead and simplify again, it seems like I just did something silly. I made things more complicated, and now I have to simplify again, like I've just added more work for myself. 3 times 1/3 x, though, well, that just gives me x. 3 times 2/3 just gives me plus 2. And on the right-hand side, 3 times 5/3 gives me 5. So I did more work here. I almost like unsimplified and then simplified again. But I got down to an intermediate step here, x plus 2 equals 5. That's a heck of a lot easier to work with than all of these fraction manipulations I have to do over here, right? Here I just subtract 2 from both sides, and I get x equals 3, my solution. So the idea of clearing fractions is I want to do a little bit of work on the front end. I want to do a little bit of work ahead of time. Investing a little bit of time and effort on the front end that's hopefully going to pay significant dividends later on. Now, it doesn't always pay off, quite this nicely. I mean, this is obviously the problem that I picked that works very nicely for our first problem. But usually it does save you time and hassle, and at the very least, is typically going to be less error prone, right? Kind of getting rid of all the fractions, doing all of the fraction stuff kind of in one step at the beginning. You can be really careful in that step, really take your time, and then the rest of the steps proceed pretty straightforwardly. So we get the same answer either way. But this right-hand side, we clear the fractions here by multiplying by 3 by the denominator that we saw across the problem. And then we just proceeded with our other steps in the general strategy from that point. Simplifying, isolating the variable term, isolating the variable, and there is our solution. So as an exercise, take this example and solve it two ways. Solve it both ways. Solve it using the general strategy, just blindly following that, right? Isolate the variable term, isolate the variable, and simplify. And then try to clear the fractions. So do the same problem a second way, trying to clear the fractions, multiplying both sides by 5, being really careful with the details to make sure that all of the expression on the left and all the expression on the right gets multiplied by 5, and try solving it that way. So take about maybe 2 minutes to do this. This should be a pretty straightforward problem. Take about 2 minutes, solve this two ways, and then we'll come back and discuss. Okay, so let's touch base here. So just like before, this problem is quite similar to the previous one. We can add 3/5 to both sides. So this is solving the first way, just the kind of straightforward way. And we get 1/5 x equals 2/5 plus 3/5 is 5/5, or just 1. And then we divide both sides by the coefficient of x, divide by 1/5. Remember that dividing by a fraction is the same as multiplying by its reciprocal, so that's the same as multiplying by 5/1, or just multiplying by 5 on both sides. So we get x equals 1 times 5, or just x equals 5. Again, it's not too terrible, although this is a pretty simple equation that we're working with here. But we can make things a little bit easier to do in the intermediate steps by multiplying by 5 on the front end. If we multiply the entire left-hand side and the entire right-hand side by 5, I do have to distribute, so 5 times 1/5 x is x, and 5 times -3/5 is -3. On the right side, 5 times 2/5 is 2, but now in this intermediate step, I have cleared all the fractions. I've got myself to where I have an equation that doesn't have any fractions in it. it's still kind of a number times x minus number equals number equation, but without any fractions. And here I can just move whole numbers around. It's a little easier, a little more manageable. I can add 3 to both sides and I get x equals 5. So again, I do a little work on the front end, and that saves me having to do the work with the fractions in the intermediate steps. Right? So over here, I had to add fractions, divide by a fraction. Now, I don't get that for free. I have to typically do a distributive property and work with fractions in this step. So I've introduced one extra step, right? There's a trade-off here. Is this one extra step worth, uh, you know, worth the benefit that I get from it? Here, maybe, maybe not. But certainly in more complicated problems, it usually is. Question 5 times 1 is 5. How are you getting x minus 3? So the 5 here has to distribute to both of these terms. It's 5 times 1/5 times x. That's 1 times x, or that's where the x comes from distributing to the first term. But then the 5 also has to distribute to this negative 3/5, the second term over here. I've kind of made a complete mess of this this bit, but 5 times the negative 3/5, you could think of it as 5 over 1 times 3 over 5, or 5 times 3 over 5. The 5's divide out, leaving us with just the minus 3. Yeah, so the 5 has to distribute to both terms in that parentheses. That's where both of these terms come from. But you are right that um, the 5 times 1/5 x does give us just a 1x. But then need to remember that other term as well. Yeah, so the benefit is that it makes this step a lot easier, right? So we do one extra step on the front end, and usually the trade-off is worth it. At the very least, having to focus really carefully on the fractions on one step, that's kind of like one area where we have to really focus because it's a little more error prone, and then the rest of it proceeds a little more smoothly. Whereas over here, I have to kind of focus on these fractions operations carefully on every step. So I think at the very least, it's probably a bit less error prone, as long as we're taking care with that first step, clearing the fractions. And in a lot of cases, it might be a little bit faster as well. So what does our general strategy look like now? Well, we just append kind of a step 0, clear fractions or decimals. We want to start off by getting rid of any fractions that might be occurring in our problem. Now, it's again important to note that this is a little flexible, right? If you strategize, I mean, if I had x minus 3/5 equals 2/5, I'm not clearing those fractions. I'm just going to add 3/5 to 2/5 and get 1, right? I see right away that that's going to work very nicely. If I have, whatever, 1/6 x minus 2/3 equals 1/2, I really don't want to deal with all that. I'm going to clear fractions there. So there's, a little bit of strategy here. Kind of similar to how, like, do we always worry about putting the variables on the side that makes the coefficient positive? I mean, it's not the end of the world if you don't, right? So there's a little bit of flexibility here, but it's kind of a general strategy. We'll start by clearing fractions or decimals. So most of the time I'll clear fractions or decimals, but especially after we're out of this section, sometimes I might, sometimes I might not, just depending on how the cost benefit seems for that problem. Okay, so let's look at this example. 3/2 t minus 2/3 equals t plus 5/3. Have something a little bit different here because I have one fraction that has a denominator of 2 and other fractions that have a denominator of 3. So what should I multiply by to clear the fractions? Right? I mean, the example up above, both examples had the same denominator everywhere. Well, I would, in some sense, like to multiply by 2 to get rid of the 2 in this denominator, and I'd also like to multiply by 3 to get rid of the 3's in the other denominators. I can kind of effect both of those at the same time by multiplying by the LCD, the lowest common denominator. What's the LCD of 2 and 3? I look at across my entire equation, both sides of the equal sign, look at all of the denominators, 2 and 3 in this case. How do I find an LCD? I take my numbers, I write out their prime factorizations, and then I say, okay, like how many kind of, I like to think of these as Legos, Lego types. I need a 2 Lego type. I need one of those to build a 2, so I need in my LCD one of the 2-sized, Lego bricks. And I need a 3 to build the 3. My LCD is simply 2 times 3 or 6. In this case, the LCD is simply the product of the two denominators, but in other cases, we might be able to come up with an LCD that is smaller, that's simpler than simply the product of the two denominators. If you don't quite remember how to compute LCDs, again, take a look back at the prerequisite material, chapter 1, or maybe some of the useful websites, and review that a little bit. But the LCD between 2 and 3 is 6. That's what I'm going to choose to multiply both sides by. So I'm going to come down here and do 6 times. Again, I better multiply by this entire left side. I want to take that whole amount of stuff that's on the left scale and replicate it and make 6 of them, right? So I need 6 times the whole 3 halves t minus 2/3 on the left. And on the right, I need 6 times the whole right side, t plus 5/3. So that's my first step. Anytime I'm doing something like this where I'm clearing fractions, it's very tempting if I'm just doing it in my head to maybe multiply like 6t and forget to distribute the 6 to the 5/3 or something. So I always write it down. I write the whole left-hand side in parentheses with the multiplying factor out in front and the same thing on the right-hand side. And then I go from there. Let me distribute on the left side. 6 times 3 halves. 6 times 3 halves. Well, that's 6 times 3 over 2. I can divide out the factor of 2 and the 6 with the denominator, leaving me with 9. And 6 times 2/3, I can divide out the factor of 3 and the 6 with the 3 in the denominator, leaving me with 2 times 2, or 4. My left-hand side just turns into 9t minus 4. I've got rid of all the fractions on the left side. I'll do it on the right side as well. I get 6 times t for the first part of the distributive property. 6 times 5/3. I lose a factor of 3 from the 6 to divide out the denominator. I'm left with a factor of 2 from the 6 times 5 is plus 10. And hey, look at that. I've got myself down to this kind of a standard form. And really our goal with this standard form is to get A, B, C, and D as integers. And we do have that. Right, so step 0, clear fraction of decimals, is done with the goal in mind of getting A, B, C, and D all as integers. So I have number times x plus number equals number times x plus number, where all of the numbers are integers or whole numbers, depending on how you look at them. And now I can just proceed as in my previous section, right? I can just go ahead and I've got both sides simplified. I can combine the variable terms together, isolate the variable term, isolate the variable. Now, one thing that we haven't really done yet, and I'll do it on occasion, sometimes I'll do it the way we have been doing it, sometimes I'll do it this way. We want to combine the variable terms and isolate the variable term. I know I want to do minus 6t, but also kind of looking ahead, I know I'm getting rid of the variable term on the right-hand side and putting it on the left. I know that I want to get rid of the constant term from the left side as well. I can actually do this all in one step if I wanted to. We're getting a little more used to working with these equations. So on occasion, I'll do these kind of two sub-steps in part two. I'll do that as a single step from time to time. If you feel comfortable doing it as a single step and you're not making errors doing it that way, go for it. If you're still a little shaky, break it into two steps, no problem there. But we'll, in this case, isolate the variable term in a single step. We'll move the variable terms to one side, and in the same step, move the constant terms to the other side. So I'm going to subtract 6t and add 4 to both sides. Basically, what I'm doing is I'm adding to both sides the entity negative 6t plus 4. Right? This is going to have the effect of pushing the constant terms onto the right side and the variable terms to the left side. I want to keep straight with what's going where, right? I don't want to subtract 6t from both sides and also subtract 10 from both sides, because that would push my constant terms and my variable terms all onto the left side. So I want to make sure that they're going on the opposite sides. And here they are. So here I see on the right side, 6t minus 6t, my variable terms go away on the right side. 10 plus 4 is 14 on the right. On the left side, negative 4 plus 4, my constant terms go away on the left. 9t minus 6t is 3t on the left. So this was step 0. Step 1, well, I suppose actually this was step 0 and 1. Clearing the fractions, simplifying, combining like terms, all of that was kind of steps 0 and 1. This was step 2 that we knocked out in a single step here. But again, if you are feeling a little bit shaky with this, combine the variable terms together in one kind of sub-step, get that answer, write it down, then isolate the variable term by getting the constant terms on the other side, write that answer down, and you'll still end up with 3t equals 14. And now we want to isolate the variable itself by dividing by the coefficient. So I want to divide by 3 on both sides, and I get t equals 14 thirds. And again, ideally, we would go back and check here. I'm not going to for the sake of time, but but if this was homework or certainly on an exam, it would be a good practice to go back and check. To plug 14 thirds in all the way up here and check that we get the right answer. All right, what about an example like this? 5/6 x plus 3/4 equals 2x minus 5/3. I have 3 different denominators here, 6, 4, and 3. Now I could clear fractions by multiplying by the product of 3 of them, 6 times 4 times 3. That's a pretty big number. 6 times 4 is 24 times 3, I think, is 72. I mean, it would work. I could clear the fractions by multiplying by 72, but that's an awful big number that I have to mess with. Let me find their LCD. 6, 4, and 3. Again, I'll start by writing out their prime factorization. To have the ability to build a 4, I need 2 factors of 2. That's its prime factorization. To have the ability to build a 3, I need 1 factor of 3. And to have the ability to build a 6, I need a 2 and a 3. 2 times 3 is 6. The idea of an LCD is, again, likening it to this Legos analogy. I like the Legos analogy, is I want to provide you with a Lego set with a collection of Lego bricks where you could build a 6 if you wanted to. You could build a 4 if you wanted to. You could build a 3 if you wanted to. But I don't necessarily have to give you enough that you can build all 3 of them at the same time, right? If I gave you a 72, then you could build like a 6, a 4, and a 3 at the same time. But that's not really what we need to do here, right? I'm kind of using this in one scenario in this term and a different scenario in this term. I kind of only need to build a 6 or be able to build a 4 or be able to build a 3. I can kind of build the 6, take the 6 apart, and then build a 4, right? I can repurpose some of the parts, in other words. So I see that I need 2 factors of 2 and 1 factor of 3. The 72 has 3 factors of 2 and 2 factors of 3. That's the Lego set I would need to give you if if you wanted to be able to build 6, 4, and 3 all at exactly the same time and have them sitting next to one another. That's not what we need in an LCD, though. We just need to have the ability to build one or the other one or the third, and we can repurpose parts. So here, 2 times 2 is 4 times 3 is 12. I'd much rather multiply by 12 than by 72. Let me multiply both sides by 12. And again, this is the step where I have to be especially careful, being careful about writing everything out, multiplying all of both sides by the LCD, in this case 12, making sure I distribute properly, making sure I handle all the fractions properly. So this is not an easy step, right? Or step 0 is not a trivial addition here. It does take quite a bit of work and effort and time to do, but putting in that time up front will make the rest of the steps much more manageable. So 12 times 5 over 6, 12 over 6 is 2 times 5 is 10. 12 times 3 over 4, 12 over 4 is 3 times 3 is 9. So I have 10x plus 9 on the left-hand side. On the right-hand side, this first term doesn't have a fraction. 12 times 2x is just 24x. The first term not having a fraction doesn't break anything. It doesn't mess anything up. Just 24x. Minus 12 times 5/3. 12 over 3 is 4 times 5 is a minus 20. And here I've completed step 0 as well as step 1. I've gotten myself into simplified form, ax plus b equals cx plus d. I was kind of there here, but here I have the added bonus that my a, b, c, and d are all integers. Now I would like to go ahead and isolate my variable term. Here I'll do it in 2 steps. I'll choose to subtract 10x off both sides. On the left side, I get 9, and on the right side, I get 14x minus 20. I've combined my variable terms together. I need to isolate my variable term now. I need to get this minus 20 off of the 14x, and I do that with a plus 20 on both sides. On the right side, I have just 14x left over by itself. On the left side, 29. So these kind of 2 sub-steps accomplish step 2, isolating the variable term, getting the number times x on one side of the equal sign and the constant term on the other side. And now I want to isolate the variable itself by dividing by the coefficient. I'll divide both sides by 14, leaving me, and I'll kind of flip the which side is which, leave me with x equals 29/14 as my answer. Right. this step and this step and this step, these 3 steps were made a lot simpler because I took this time and effort to put in to step 0 and clear my fractions, right? Try doing this one without clearing fractions. If you want an exercise in working with fractions after class in your notes, um, go and try to do this one without clearing fractions, and you'll see how cumbersome it is, right? You're going to have to combine a 3/4 and a 5/3 together. You're going to have to combine a 5/6 with a 2. You're going to have, fraction times x equals fraction. You're going to have to invert and multiply. There's a lot more pieces and components that you have to remember if you do it that way. So even though I, typically don't mind working with fractions, it's not a big deal to me. I'm used to it by now. Um, you know, it, if you gave me this problem to solve, I would do it this way. I would clear fractions first because it makes all of these steps not only faster, but also less error prone. I'm less likely to make a mistake in the next 3 steps because I've done this one step. Now, this one step is an error prone step, so I really have to pay attention here, make sure I do everything really carefully. So I do really have to pay attention in that first step, but then it makes the rest of the problem a lot easier. I'd rather have one error prone step than 3 or 4 of them. Okay, so 2 exercises now, a simpler example and then a more complex example. Uh, Take a bit of time to work on these. Let's shoot for maybe 3.5 minutes for this first one, and then we'll come back and touch base. Um, and if you get done with the first one in under 3.5 minutes before we come back, then you can start working on the second one. But we'll work through the first one, come back in 3.5 minutes, go through that answer so that if anybody's really stuck, you have a chance to ask questions or to kind of see how it's done. And then we'll move on to the second one after that. So 3.5 minutes, we'll come back. Okay, it's right around 3.5 minutes. So, um, any questions on this one? Any thoughts on this one? So the LCD here turned out to just be 7 times 5 because our denominators 5 and 7 are actually both prime numbers. So the LCD is kind of to build a 5, we need a 5-unit Lego, and to build a 7, we need a 7-unit Lego. So I just have to give you both a 5 and 7-unit Lego. So the LCD turns out to be 35. Multiplying both sides by that, simplifying gives us 5t minus 14 equals 35t plus 7. And here we can get the variable term on the right-hand side with a minus 5t, and maybe in the same step, if we're comfortable, get the constant term on the left side by subtracting 7. I know that I want to move the plus 7 because the t's are going to end up on the right side. I want the constant terms on the left side, so I got to move that plus 7 with a minus 7. On the left side, the t's go away, and I get negative 14 minus 7 is negative 21. Be careful with your minus signs there. Make sure that everything's kind of going in that same direction. And on the right side, my plus 7 minus 7 goes away. 35t minus 5t is 30t. Now I have 30t equals negative 21, and I divide by the coefficient. I have successfully isolated my variable term. I want to isolate the variable, divide by 30, and I get t equals negative 21 over 30, which I see can simplify down to t equals negative 7 over 10. Any questions on that one? All right, let's take about, maybe I'll leave this one up for just a couple minutes. Let's take about 4 minutes to work through this one. And again, be careful with that LCD that, you know, we don't want to just use 10 times 4 times 5. That would be overkill. What's the lowest common denominator we can get away with using? Sorry, was there a question? I didn't catch that. Okay, let's take a look at this one. So again, if I just kind of naively multiplied my denominators together, I would get 10 times 4 is 40, times 5 is 200, quite a large number to deal with. But if I break down my 10, 4, and 5 into their prime factorizations, 10 breaks into 2 times 5. So I kind of need like one 2 building block and one 5 building block to make a 10. For 4, I need two 2 building blocks, and for 5, I just need a 5 building block. So actually I can get away with just a Lego set, so to speak, consisting of two 2 blocks and a single 5 block. How do I know which 2 to use in the LCD? Um, well, so I kind of have like a first 2 that I need for the 10, but then the 4 needs two 2s. So I have like a second 2 popping up for the 4. Um, if you imagine like literally having a Lego set consisting of 2 blocks of size 2 and one block of size 5, how could you combine like a 5 with a 2? Well, you could actually use either 2, right? I could either think of this as being combined together to make the 10, or I could think of this as being combined together to make a 10. It doesn't really matter. But the important thing is that my 4 requires a size 2 building blocks. Okay, there's a question. Are you splitting 35 by 1/5? How are we turning 35 to 5t? Okay, yeah. So okay, so I think that is a question from this one up here. Yeah, so let's jump back here. This is 35 times 1/5. So 35 times 1/5. Well, that's 35 over 5 is 7. And that's because 35 is just 35 over 1. And then we multiply the numerators, multiply the denominators. And 35 is 7 times 5, right? So our 5s divide out. So I think that answers the question in the chat. Yeah, so for this one, we see our LCD 2 times 5 times 2 is 20. And so that's what we want to multiply both sides by. I think I've got all the questions in the chat, right? Okay, yeah. Yeah, so we want to multiply by 20 on both sides. Again, being just super careful that number one, we take the entire left-hand side in parentheses, multiply by 20, same with the right. Yeah, exactly. When we're multiplying by an integer by a fraction or fraction by an integer, we kind of implicitly think of it as being like an over one kind of a situation. And same thing down here, right? We're thinking of this 20 kind of being like a 20 over one when it's multiplying onto these fractions. Yeah, good question. So here I have 20 times 3/10, or I can think of that as 20 over 10 times 3, right? A times B over C, I could think of as A times B over C, or I could think of as A over C times B. So all of these mean the same thing. So I can do the 20 divided by 10 first, making it 2, multiplied by 3. 2 times 3 is 6x. 20 over 4 is 5 times 3 is 15. So 6x plus 15 on the left. And on the right side, 20 times negative x gives me negative 20x. And 20 times 1/5, what's 1/5 of 20? That is just 4. Negative 20x plus 4 on the right. This completes steps 0 and 1. I've gotten myself into a standard form with just integers as the coefficients. And now I can work on getting my variable terms together. I'll do that in 2 steps here. I could do it in 1 step, could do it in 2 steps, just depending on comfort level. I'm going to add 20x to both sides because that's going to give me a positive 26x on the left, and that keeps my coefficient positive, a little nicer to work with. So it gives me 26x plus 15 on the left, and then just 4 on the right side. I need to get rid of my plus 15 on the left. So I subtract 15 off both sides. 4 minus 15 is negative 11. And I just have my 26x by itself on the left. I've isolated my variable term now. And then to isolate the variable itself, just divide by that coefficient of 26, and I get x equals negative 11 over 26. 11 is prime, and 26 is 2 times 13. No common factors to divide out, nothing to simplify. That is my final answer. Any questions?
Yeah.
Yeah.
So I ended up with 11 over negative 26 because
Mhm.
where you do plus 20,
Yep.
I did plus 6 and went that way.
Yeah, that's fine. So, yeah, so when we have a negative attached to a fraction, it's actually a little bit like this if you just took a to be -1. So, like negative a over b is the same as negative a divided by b is the same as a
Yeah.
divided by negative b. These all are just different ways of writing the same thing. We could have the opposite of the fraction a over b. We could have the opposite of a divided by b, or a divided by the opposite of b. All mean the same thing.
Okay.
Yep. Yeah, it's because the product or quotient of one negative with one positive ends up being negative. So whether I take this one to be negative and this one to be positive, this one negative and that one positive, or just have an overall
Okay.
negative. Yeah, it's all the, yeah, it's just different ways of writing the same thing. Yeah, so I mean, I wrote it this way. I could have just as easily written it as negative of 11 over 26 or as 11 over negative 26. Yep. Yep. Yeah, and yeah, so that's fine if you had gone this way by subtracting the 6x, got negative 26x equals positive 11. Uh, yeah, that would have been kind of the more natural way to get the negative on the bottom there. Yeah, good question though. Any other questions? All right, so let's look at an example like this one. Now here I have an equation. I have fractions on both sides. I could go ahead and multiply by the LCD. I could multiply by 15 on both sides. And there's nothing inherently wrong with that. But I might look at this, right? If when I get more used to these equations, I might start trying to look a step or two ahead. And I might actually recognize that 1/5 actually meshes pretty nicely with 5x and with -10. And actually 1/3 meshes pretty nicely with 6x and with 9. I don't have to follow this general strategy completely rigidly. As long as I'm doing valid algebraic steps, valid equation solving steps, there is freedom here, right? Now I can't do illegal things. I can't like add 5 to one side and add 7 to the other side and think that I still have a balanced equation. But I don't always have to clear fractions. That's not, a requirement. And in fact, in this case, if I distribute the 1/5, I see 1/5 times 5x is just x, minus 1/5 of 10 is 2. And if I distribute the 1/3, 1/3 times 6x is 2x, 1/3 times 9 is 3. It actually turns out to just be a perfectly nice equation. I don't have to go through all of this multiplying by 15 and getting a factor of 3 left over here, a factor of 5 over there, multiplying through, getting a bunch of big numbers, dealing with all that. It's actually easier to just deal with this as it is and just simplify both sides. Subtract x, I get -2 equals x plus 3. Subtract 3, I get x equals -5, and there's my answer. So I don't always have to rigidly follow my strategy. My strategy is a guide, but if I realize that there's a shortcut, again, so long as I'm being very careful to do all of my arithmetic, my algebra, my equation solving steps properly, as long as I'm making valid steps, if I notice a shortcut, I can take a shortcut, right? You're not going to like lose points or the answer is not going to be wrong because you didn't clear fractions first. Clearing fractions is a tool. It's one tool in a toolbox that's meant to be helpful. But if you realize that maybe in a case like this, it's actually easier to not clear fractions, it saves time and effort and complexity and even error proneness to not clear fractions, then go for it. Again, so long as you're being careful and making valid algebraic steps, valid equation solving steps, and so on. But I could have a situation like this where, this kind of 2x plus 3 all over 8, the 8 kind of meshes, I guess, maybe a little bit okay with the 2x, but not with the 3. The 5x plus 1 over 2 can't really be simplified at all. So this is a situation where I definitely would like to clear fractions. Let me actually bump this down one line. There we go. When it's on a different line, especially with these fractions like this, it makes everything a little bit bigger for you. So looking to solve 2x plus 3 all over 8 plus 3/4 equals 5x plus 1 all over 2. So here I will clear fractions. What's the LCD of 8, 2, and 4? Well, these all just have building blocks of size 2. So I see that my Lego set just needs 3 building blocks. It's just going to be LCD is 8, right? 2 times 4 is 8, 4 times 2 is 8, and 8 times 1 is 8. So that's just my LCD. I want to multiply both sides by 8. I have to be a little bit careful here. This 2x plus 3 over 8 is kind of like a 1/8 times 2x plus 3. Similarly with the 5x plus 1 over 2. So I just want to make sure that I'm being careful when I'm doing this distributive property. So I see that I have 2 terms here. I have this thing being added to this thing. The 8 needs to distribute into this term and into this term. Right, this can be a somewhat challenging distributive property because the 2x plus 3 almost looks like it's 2 terms, but because that's in the numerator and the overall operation between the 2x plus 3 and the 8 is the whole 2x plus 3 is being divided by 8, we're going to consider that just one term. Again, maybe another way to think about this is like 1/8 times 2x plus 3 if you're not seeing this right away. But 8 times 2x plus 3 over 8, that's what I get from the first distribution. Distributing the second term, I get 8 times 3 over 4. And on the right side, 8 times 5x plus 1 over 2. Again, if you're not following these fractions operations, go back and review fractions. If you're struggling with this, go back to that chapter 1 material or to some of the reference material and review these fraction operations, drill some of these types of problems, and just through drilling, get a little more up to speed with it, and that'll help a lot. But here I see I have 8 divided by 8. They go away, and I just get 2x plus 3. 8 divided by 4 is 2. 2 times 3 is 6, so that's a plus 6. And on the right-hand side, I have 8 divided by 2 is 4 times 5x plus 1. So I've cleared my fractions. I've got step 0 done, but I've still got some work to do for step 1 to get things into ax plus b equals cx plus d. I want to distribute again, combine like terms, simplify everything. On the left, I have 2x plus 9 And on the right, when I distribute, I have 20x plus 4. So after this next simplification, I've got step 1 done. I'm ready to go. I've got everything into my my standard form, ax plus b equals cx plus d. And I have variable terms in 2 different places. Let me combine my variable terms together. 20x minus 2x is 18x. And maybe in the same step here, we will move our constant term onto the left, minus 4 on both sides. So I have 18x equals 9 minus 4 is 5. I've now got step 2 done, isolating my variable term, getting my variable term by itself. And then I isolate the variable itself by dividing by that coefficient, dividing by 18. I have x equals 5 over 18. Any questions so far? All right. I think we're going to come back to these exercises. Oh, I actually forgot to change this one. This was actually a duplicate of the previous one and forgot to change it. We're going to come back to the exercises, I think, next time because I want to knock out one of these decimal problems today. So maybe we'll shuffle things up just a little bit and we'll finish up this section next time. So let's take a look at this equation with decimal coefficients. I'm looking to solve 1.7x minus 3.2 equals 4.8x plus 9.1. Now, again, we've seen a decimal equation in the past, lecture or two ago. We could just go ahead and combine our variable terms together, isolate the variable term, isolate the variable, but we're working with decimals. Decimals are a little more challenging to work with than whole numbers or integers. So doing decimal addition or subtraction, or certainly decimal division, is maybe just a little bit more challenging. Can I get rid of my decimals? Can I turn my decimals into whole numbers or integers? Keep in mind that when I have a decimal, like let's just say 9.1, for instance, well, I kind of think of 9.1 as like, say, 9.1 over 1 or 9.1 over 1.0. And I know that I can multiply kind of top and bottom by 10. Multiplying by 10 over 10 doesn't change the value, it's just multiplying by 1. And that would bump the decimal place one place to the decimal point one place to the right, both in the numerator and denominator. Right? 9.1 is the same as 91 over 10. Or like if I have 91, or sorry, if I have $9.1, that would be like having 9.1 dime, or set it backwards. If I had $9.1, that would be like having 91 dimes. So I could think of 9.1 as 91 over 10. So in other words, when I'm thinking of kind of multiplying by an LCD, so to speak, here my idea of LCD is how many decimal places do I need to move to the right to essentially make my decimal disappear, right? 9.1, if I move that decimal point 1 to the right, that becomes just 91.0 or just 91. I don't have to work with my decimal anymore. Of course, it's still a decimal number, strictly speaking, but I see I have to move one place to the right, one place to the right, one place, and one place. If I move one place to the right in each of these terms, I'll have gotten rid of all my decimals. I want to multiply by 10. 10 to the first power, because I want to move one place. If I needed to move 2 places, I'd multiply by 100, 3 places by 1,000, and so on. When I distribute, 10 times 1.7 is just 17x, minus 10 times 3.2 is 32. On the right side, 10 times 4.8x is 48x, plus 10 times 9.1 is 91. Be really careful. I didn't like say that 9.1 just turns into 91, right? I didn't just make 9.1 91 because I didn't want to deal with the decimal. I went through this process of multiplying both sides of the equation by the same number, 10. So that's a valid equation solving step. And that leads to a simpler equation. I've cleared the fractions or decimals in this case, and it ended up in standard form. Now I can subtract 17x from both sides. The x's go away on the left, leaving me with just negative 32. And on the right, 48 minus 17 is 31x plus 91. I want to isolate my variable term, so I subtract 91 from both sides. 31x, 32, or negative 32 minus 91, that is negative 123. I have bigger numbers in an absolute sense to deal with here, but I don't have any decimals to keep track of. And essentially the operations are no more complex, even though the numbers look bigger and in an absolute sense are bigger. I still have the same operations to do. If I was doing negative 3.2 minus 9.1, I'd still have to do the same operations, but also keep track of a decimal point. And then lastly, I isolate my variable, dividing by the coefficient, and I get x equals negative 123 over 31. And 123 is what? 41 times 3. 31 is prime. I have no common factors, so nothing simplifies any further. That is my answer. Not the prettiest fraction ever, but that's the answer. Okay, so when we come back next time, we will hit a couple of last exercises in fractions and decimals, and then we'll move on with the next section. Are there any last questions before we break for today?